Welcome back. Today we're going to discuss the adoption of IPv6. But unlike previous discussions where we talked about the state of IPv6 deployment, here we're primarily interested in how we can measure IPv6 deployment. So we'll be looking at a paper by the good folks at Takeda, Simula, and Ripe, and the methods that they use to measure the deployment of IPv6 infrastructure, specifically from the standpoint of the routing and topology. We should note that there are many different ways to measure IPv6 deployment, and you may get a very different view of the availability of IPv6 depending on how you measure it. But in general, we can say, just as when this paper was written, IPv6 will be deployed any day now. As we've talked about before, one of the primary motivating factors for deploying IPv6 is that we don't have enough IPv4 addresses. And in fact, all of the available IPv4 addresses have been allocated at this point. This shortage was anticipated decades ago, and led to the development of IPv6, which has a vast address space compared to IPv4. Shortly after it was standardized, the operating systems and network hardware were upgraded to support IPv6. So in that sense, the protocol is not new and is quite mature and widely supported. The problem preventing its rapid adoption, however, is that IPv6 is not backwards compatible with IPv4. So a host running one protocol can't communicate with a host running the other protocol. It's also the case that the configuration and management of IPv6 infrastructure has some substantial differences from how we are used to managing IPv4 infrastructure. Note that when we say that v6 is not compatible with v4, it literally means they can't communicate directly with one another. It is, however, the case that a host can run both simultaneously. These are called dual-stack devices. We'll mention that again later. So looking at growth of v4 compared to v6, obviously, v4 growth started much sooner, and the v6 growth is minuscule by comparison. Note that this is growth in terms of the number of autonomous systems supporting each of the protocols. However, if we zoom in the v6 curve, so note that the v4 curve and the v6 curve are plotted against different y-axes here, we see that IPv4 went through an exponential growth phase, and it appears that v6 is currently in its exponential growth phase. So from that perspective, there's some similarity here to the pattern. So the question then is, what's contributing to this growth? We could look at it from the types of businesses that comprise these different autonomous systems. We could look at geographic regions. And we also have to wonder if v6 performance is comparable to v4, or if there's a trade-off favoring one or the other. So for this work, the authors used topology snapshots from BGP routing advertisements dating back to 1998, making this what we would call a longitudinal study. They also annotated the AS topology with business relationships, designating the two ASs on each peering link as peers or customer, provider, and so on. The details of that annotation are covered in other papers. Autonomous systems are also annotated by their business type, in this case narrowing it down to transit, content versus access, enterprise customer, as well as their geographical region. To measure performance, the authors measured web page downloads and the associated AS paths, so they measured performance from various ASs to the Alexa 1 million most influential websites, or at least the subset of those sites that supported both IPv6 and IPv4. As an aside, let's talk a little bit about the business types that these ASs fall into. And we note that BGP peering corresponds with business relationships. The tools that we have in the BGP protocol are primarily designed to implement policy, and that policy reflects the exchange of money between the businesses in question. Here we show dashed blue lines representing settlement-free peering links, meaning the two ASs are relatively equal and exchange traffic for mutual benefit. Then we show the green arrows representing the flow of money from a customer to a provider. So those peering links are not between equals, but the smaller AS pays the larger AS to carry their traffic. So we see that both enterprise customers and universities, as well as content networks, pay ISPs to carry their traffic, and then we have the mid-level regional ISPs that pay Tier 1 ISPs to carry their traffic. In the terms that we'll be using in this paper, we have large transit providers corresponding to Tier 1 ISPs, and then we have small transit providers corresponding to the regional ISPs. Then we have the content access and hosting providers, and the enterprise customers. Note that this is a very simplified hierarchy, and in reality there are many BGP peering links that don't neatly fall into this structure, but that's a topic for a different day. So some high-level results up front. IPv6 deployment is strong in the core and lagging at the edge. And this is not too surprising, given that it is relatively easy to turn on IPv6 on dual-stacked routers, and the configuration is not too much different than what we're used to with IPv4 routers. However, at the edge, where middle boxes are a much larger part of the network, the configuration and especially concern for security and firewalls can vary greatly between IPv4 and IPv6, and so the enterprise customers tend to be more hesitant to turn on IPv6 on their networks. Another result is that the performance between the two protocols is similar, and we would expect this if the infrastructure is primarily dual stacked as opposed to new hardware being deployed along with IPv6. But perhaps somewhat surprising, at least at the time of this study, is that less than 50% of the AS level paths are identical, meaning the business agreements between ASs are not necessarily being updated to include IPv6, even when both ASs involved in the agreement support IPv6 internally. In this study, they showed that 70% could be identical using only the existing peerings, and that could be even higher with new peerings between ASs that already support IPv6. So this also means that there are differences in the deployed policies between IPv4 and IPv6. Now we come to the longitudinal portion of the study. And on the top graph, we have IPv4 ASNs, and we see that the majority of the ASNs are enterprise customers. Probably second largest is small transit providers. Then we have content and access networks, and the number of large transit providers is so small that it doesn't really show up on these graphs, but they do exist. So reflecting the conclusion on the earlier slide, we see that the lower graph, IPv6, is much more biased towards the small transit providers and content and hosting, and has a much smaller fraction of enterprise customers relative to IPv4. So that's where the conclusion about the enterprise customers lagging behind in deploying IPv6 comes from. But we do see that as we move to the right in time, the fraction of enterprise customers is catching up. So this is a sign of IPv6 being adopted. If we think back to the initial rollout of IPv6, of course, there would be the chicken and egg problem, where there's not much motivation for an ISP to deploy IPv6 if none of their customers demand it. And there's not much motivation for a customer to deploy IPv6 if their ISP doesn't support it. So seeing this trend in the lower plot indicates to us that that chicken and egg problem has been overcome, and there is now an increasing rate of enterprise customer deploying IPv6, which presumably means that they have ISPs available to them to connect via IPv6. Continuing with the longitudinal study, we look at geographic regions. And so we're looking at the numbers of ASs deployed in 3 different RIRs, ARIN, RIPE, and APNIC. So we can see that there was an early exponential curve in all 3 of the RIRs for IPv4, and then that they went into a linear growth phase, although the RIPE exponential growth phase lasted much longer than the other 2. Then when IPv6 ASs begin being deployed, we see that they go through a similar exponential growth curve. And by the time we get to the right side of this plot, even though V6 and V4 are on 2 different Y scales, the ordering is the same. RIPE has the most ASNs, ARIN has the second most, and APNIC has the least. So this seems to imply that there's a convergence in the number of ASNs supporting the 2 protocols within each of the RIRs. We can also note that while RIPE initially lagged ARIN in growth of V4 ASs, RIPE has always been ahead of ARIN in IPv6 ASs. We can also break this down by the fraction of the ASs that are present in IPv6. So in the top graph, we can see this broken down by business type, where the large transit providers are approaching 1 or 100% adoption of IPv6. And the content and hosting providers have just made it up to 50%, with the small transit providers slightly behind them. However, the enterprise customers are only at a 10% adoption rate. And thinking back a couple of slides, we know that enterprise customers are the vast majority of ASs in total. Breaking it down by geographic region, we see that all of the regions follow a similar trajectory. However, APNIC leads as far as the fraction of ASs, followed by RIPE, with ARIN trailing behind. For the 3 measures we just looked at, we can think of those as quantities. How many ASs are participating in IPv6 relative to IPv4? But now we can look at this at a finer level of granularity, meaning the structure of the AS paths themselves, which we can think of as a quality measure. How rich is the IPv6 topology relative to the IPv4 topology? The theory here is that IPv4 is the much more mature protocol, and so as IPv6 matures, it should become more and more similar to IPv4. To do this, the authors used AS level paths from 7 different vantage points around the internet and looked at the AS paths between those vantage points and the origin ASs. So they want to see how many of the paths are the same for both IPv4 and IPv6. So again, we're looking at the progression through time, and we have some interesting stuff going on. So we're plotting this as a fraction of AS paths. So we have all the IPv4 AS paths, and then we're seeing how many of the IPv6 AS paths are the same and how many are different. Each curve is plotted from a different vantage point. So the interesting thing that we see going on here, while across the board the fractions increase, we see that HE, Hurricane Electric, had a very low fraction up until mid-2007, and then took off, rapidly eclipsing all of the other vantage points seen here. And that reflects a very aggressive push by Hurricane Electric to set up IPv6 peering with as many other ASs as possible, including through tunneling. But in general, across the board, we see an upward trend where more and more of the AS paths are becoming the same between IPv4 and IPv6 over time. So while in absolute terms, when this plot was made, the average was less than 50% identical paths, it is progressing towards convergence. Now we come to the performance discussion. We would hope to see similar performance between IPv6 and IPv4. We would not expect a large improvement in performance, even though there are some changes in the protocol that are geared towards improving performance. However, there are other trade-offs that were made, such as the larger header. But we do know that if performance in IPv6 were significantly worse, that would be likely to inhibit adoption. So in this case, they're using 5 vantage points to request web pages over v4 and over v6 and comparing the download times. In the background, they're also using trace routes to compare the AS paths to those websites. So here we're plotting a CCDF showing whether v4 was faster or v6 was faster, and also annotating whether the paths are the same or different. We're counting performance within plus or minus 10% as being roughly equivalent performance. And we can see that when the paths were the same, about 80% of those paths had similar performance between IPv4 and IPv6. However, when the AS paths were different, a smaller fraction of the paths had similar performance. And as we mentioned before, less than 50% of the paths from dual-stacked vantage points are currently the same. And in general, those differences favor IPv4 performance due to the IPv6 topology having fewer connections. Then the authors went on to study the potential AS path congruence. So not the current path similarity, but if all the peering agreements were made that could be made given the ASs that currently support IPv6, how many of these paths could be identical? And we see that over time, those fractions are a bit higher than the fraction that we see in practice. In the case of the Hurricane Electric vantage point, up to 70% of those paths could be the same. We also see that that fraction could be even higher if ASs establish new peering agreements over IPv6 that already support IPv6. This would be seen as a recommendation about who should peer with whom to improve the richness of the IPv6 topology. Lastly, we can look at the stability of the routing, meaning how long does it take to converge when there are changes in route advertisements? And we would like to see these becoming more and more similar over time, and it appears that is what's happening. We note, however, that due to the sparseness of the IPv6 topology relative to IPv4, outages or changes that take a long time to converge for just a couple of ASs can affect the overall averages significantly. And that's where we see significantly more noise in the IPv6 curve here than on IPv4. But in general, in steady state, the convergence times and updates per event are similar for IPv4 and IPv6. So for these authors, the summaries are about the state of IPv6 adoption. And of course, in the intervening years between this publication and today, that adoption has continued by various metrics. For us, though, the takeaways are looking at a number of the techniques that the authors used to perform their measurements. And in particular, one of the key things that they did is to correlate data plane and control plane measurements. So they were taking measurements based on BGP advertisements, that's the control plane, as well as the history of BGP advertisements, and they were correlating this with data plane performance. So the data plane measurements include the trace routes that they performed between vantage points and websites, as well as measuring the performance of downloads over HTTP. Without correlating these measurements from the data plane and the control plane, they would only be able to tell part of the story, such as being able to show that the paths are different, but not whether it was helping or hurting performance. And vice versa, they might be able to show a difference in performance from the data plane without knowing whether it was related to a topology difference or not. That's all for now. We'll see you on the next one. We hope you enjoyed this video. If you found it to be useful, please click the like button. To be notified when more videos are posted for this class, please subscribe to our channel and click the bell.